Hi, my name is David Barroso. I'm a principal engineer in the network systems team at Fastly, and I'm going to be talking today about how we manage our presence on the internet. For those that don't know anything about Fastly, very short introduction. We're a CDN. We power sites like GitHub, Twitter, Shopify, Vimeo, Pinterest, Imager, and many others. We have around 57 POPs, 22 terabits of connected capacity, and we do around 7.5 million requests per second at any given time and 5 terabits of internet usage. So let's start talking about connectivity. What is connectivity? Connectivity is, according to the dictionary, the ability to make a connection between two or more points in a network. You need basically two things. You need a source and a destination. Well, looks easy enough. I don't know what the fuss is about, so let's just go home and watch Game of Thrones, right? Well, not really. Like, we're all network operators. We know that things are not that easy. So let's imagine for a second that this is the internet. We have a bunch of networks connected to each other. We have a few POPs with very funny cat GIFs, and then we have a user. So the first thing is that the content needs to be reachable by that user. So if the user asks for one of those funny cat GIFs, it knows where to go and find it. And then finally, the cat needs to reach the computer somehow. So from a content provider perspective, it's actually two independent things, right? Like you need an inbound path, which is how you as a user can reach my content. And then there is also the outbound path, which is how can I serve the content to you. We are all pretty familiar with BGP here. BGP is the protocol that we use on the internet to provide reachability information. And basically, with BGP, you would be working with, well, getting all that reachability information, right? Like you can advertise your networks so others know how to reach you. And you can also receive from peers their networks so you know how to send the content back. For the sake of this talk, we're going to be focusing only on how to reach users, not how users reach the content. So BGP is great, but there are at least 4 things that BGP doesn't care about. Number 4 will shock you. The first one is packet loss and jitter. Like BGP will tell you how to reach a particular destination, but it won't tell you the quality of that particular path. Like if there is internet weather, or if there is congestion or something else going on the internet, like BGP won't signal back to you. Latency is another thing that BGP doesn't know anything about. Like, just imagine for a second that you have like 4 routers connected back to back in the same building. That's from a BGP perspective, that's going to be like 4 hops. While if you have like 2 routers connected back to back, but one is sitting in Europe and the other one is in the US, like BGP is going to think that single hop, that single AES in the AES path is way better than those 4 other hops that you have in the same building. But that's not true, because we all know how the speed of light works. So BGP is not like ideal for this kind of problem. This is becoming even more problematic as people start doing like remote peering on IXPs. Because you usually trust like, oh, I'm peering with this person directly, so I'm going to assume that the path is like super short, but that's not true anymore in most cases. Another thing BGP doesn't care about is cost. Like you all know that transits will not have the same price. If you're peering with someone, that's going to be way cheaper than using transit, etc. And then finally, like DDoS attacks. Like BGP doesn't know anything about light bulbs just being compromised and destroying some part of the internet. So now let's just jump onto like inbound TE challenges. The first challenge with traffic engineering on the internet is what I call fog of war. It's like one of those real-time strategy games where you can only see the region that you control. So with the internet, it's the same. Like you can connect to your devices, You can check your own policies. You can see what prefixes you're sending to your peers. But there is no way for you to actually check your transits policies. So you don't know exactly how your changes, your traffic engineering changes, are going to affect their network. And of course, like things multiply as your transit then will propagate those announcements to someone else, and that someone else to someone else, and so on, so forth. When doing traffic engineering changes, you can do things like, oh, dear transit, do not send this particular prefix to this particular region of the world, or do not announce this prefix to this particular ASN, or can you please prefer this path over that other path? Those are features that you may find on some transit providers. You may not find them on some others. So there is no standard feature set. You have to manage that somehow and be aware of which transit provides which features. What's even worse is that even in the case where they provide the same feature set, implementation is different. Like they may have like different communities to signal that, or they might use like even different set of communities. Like some may require like just like one community, some others may require like 2 or 3 communities, and things like that. So now we put fastly scale into perspective. We have 57 POPs, as I mentioned previously. We have 4 edge routers per POP. Then we have on average around 100 different connected networks per edge router, of which 50 globally may be unique providers. By providers, I mean things like global or regional transits, IXPs, etc. And they all have like different T features and implementation. And then on each one of those peers, we need to announce around 30 different prefixes. So you start multiplying things, you realize that we have to generate around 700,000 different announcements globally. So that's a lot. And so you have to announce all those prefixes, and all those prefixes are going to look similar, but not quite the same, because they're going to have like different communities and different attributes depending on the region connectivity. Like it's not the same announcing a prefix in Asia or in Europe. And also depending on the network that is being announced to. So I was mentioning before, you want to do like T changes, you will have like a set of communities on one peer, while you will have another set of communities on another one. And now you're operating that network, and there is a DDoS attack, or there is like some connectivity issues somewhere in the world, and you have to start tweaking not all of those announcements, but some of those announcements. So yeah, it's no surprise that every now and then things like this happen. Like there is some transit that just makes a mistake, and all of a sudden, like half of the internet blows up. In my opinion, this is not like an engineer error. So I don't think he or she is to blame, but the tooling is to blame here. Like you should have tooling that prevents these things from happening. So in summary, inbound T is kind of like the art of pretending that you understand what you're doing and how your actions are going to affect the global internet, where you have no visibility and no control. So you start just attaching a bunch of communities, you prepare your own AES in the AES path, and you basically roll a dice and hope for the best. So yeah, now we are all depressed about the state of the internet. So let's try to talk a bit about how we try to solve this at Fastly. So the objective is to build an orchestration system that allows us to operate the network as simple and as safe as possible. That was kind of like the promise of SDN. We're still waiting for it. So what do we need? To begin with, we need a system that can orchestrate the changes. Like as an operator, I don't want to care about to which devices I have to connect to if I want to do a change in Europe. Like I may have like 100 different of them, so I don't want to start SSHing into all of them, because I may end up even SSHing into the wrong device and doing the changes somewhere else in the world, causing like massive problems. I also don't want to bother as an operator about the details of the change. Like I don't care if this provider uses this community, about if that other provider uses that other community. I want that thing to be abstracted away from me. Like I want to prevent this traffic to traverse this part of the world. And then finally, we need to ensure that we have at least some safeties to minimize the chances of failure and mistakes. So let's start talking about the orchestration part. So let's imagine this is your network. Like you have a few POPs distributed all across the world. So the orchestration part is quite simple, right? Like what you want is just like a central location where you do changes, and changes are propagated everywhere on your behalf. And if you just want redundancy, you just duplicate this service and duplicate the data. So the first thing you have to decide is how to build this system. The system needs to connect to hundreds of devices, regardless of location, and it has to be able to process hundreds of thousands of messages. So you could start building your own thing. Like there are many protocols out there. You could use gRPC, Thrift, Message Pack. You could use Unicorn Tiers. Seems to work very well. Or you could use BGP. Like, I mean, BGP seems to fit the bill here. Like we know that it scales to to millions of routes, and we know it can connect to many hundreds of devices because we are doing that in production. So using BGP has a few advantages. The first thing is that it works out of the box. There are plenty of open source options that you can start leveraging on. Like you have BERT, you have Quagga, you have XBGP, GoBGP. There are even some written in Perl. I'm sorry for them. But it has also a few disadvantages. Like the main one being that you are now constrained to BGP updates as your messaging. So you will only be able to do what you can express on a BGP update, which means that you cannot do things like, oh, can you shut down this peer? But that's fine. Like building systems in the microservice fashion means that you just need to solve one problem at a time. Like if we needed to expand this to something else in the future, we could just add another system in there. Now, let's see which open source BGP options we have out there that we could use for this use case. So there is XBGP. XBGP is pretty nice. It's very programmable, written in Python, so it's very easy to use. The problem is that it doesn't really scale well. Like we were doing some tests initially, and it was taking around 5 minutes only to establish the connection to all of the devices on the network, which is not okay for this particular use case. Like we want something that is like super, super fast because we need this under like stressful conditions, like a DDoS attack and whatnot. GoBGP is really nice as well. It had some minor problems when we started evaluating using GoBGP for this use case. However, the community behind GoBGP is great, so after a few conversations, we managed to solve those issues. From a scalability perspective, it's quite good as well. Like memory consumption was quite high, but this is running on a server, so it's not of a huge concern. And the processing of all the prefixes and whatnot was measured in tens of seconds, so it was quite good. Then there is BERT. The thing about BERT for us is that it's what we use in production, so we are super familiar with BERT, like both as operators and as contributors of the open source software. So this kind of felt to us like the best choice. Also, from a scalability perspective, it's like it's the best project out there. Like RAM and CPU consumption is super low. It's super fast processing everything. It doesn't have an API. That's kind of a bit of a problem. But it has a very expressive configuration language, so it kind of compensate. You still have to parse all the output if you want to gather information from it, but that's a minor thing. So in the end, we decided to go with BERT because of all this experience that we had and the scalability. There are other solutions there, but at this point, like, who cares? Like, at some point, you just have to draw a line. Otherwise, you're going to spend like 6 months of the project just like evaluating all the potential options. So yeah, so we have a winner here. Like, we're going to build this orchestration system using BGP, and we're going to build it on BERT. So now let's start like talking about abstractions. Like, what does this service has to provide for the operator to operate the network in a safe fashion? So obviously, you're building a system for operators, so you have to talk with them, right? Like, you're not going to be building just something because you think it's cool. So you start this conversation like, OK, what do you need to do? Like, well, I need to announce services. Like, OK, where do you need to announce these services? Like, well, it's usually on a particular region, sometimes on a site, or in very rare cases on a specific switch. OK, you need to announce services. How do you do that? Well, BGP updates. Like, that's kind of how I signal transits and peers that I need to, like, I want to announce a service. And those BGP updates may have different attributes depending on what I need and want to do. OK, you mentioned providers and peers. What does exactly mean? Well, a provider for us is someone that owns a connection, a circuit. Like, could be like a transit, like NTT, Telia, whatnot. They own they usually own the circuit and the BGP station. But there are other cases like IXPs where you have like, I don't know, AMP6, links, PLICs, that they own the connection. But then behind it, you are peering with other people. So that's why we distinguish between providers and peers. And then finally, you have to kind of like, OK, what are those BGP attributes for? Like, well, attributes are mostly to signal our upstreams whether we want to do something or not. Like, yeah, do not advertise this prefix to Asia, or don't advertise it to this particular ASN. OK, so we have identified like a few abstractions now. We have services, which is these are the prefixes that I want to announce. Location, which is where do I want to announce these particular services. Then we have also targets, which is the peer group provider pair that we want to send the updates to. And then finally the actions, like I want to do this, I don't want to do that other thing. So we start mocking a user interface for the operator. Like, we have the service that we want to announce. This is just a name. This will translate to one or many prefixes. The operator doesn't really need to care about those prefixes. It doesn't have to care either if it's IPv4 or IPv6. Like, the system will just like resolve that on the operator's behalf. And then you can start like describing what you want to do. Like, for instance, like globally, I want by default to announce this set of prefixes over NTT and Telia. Then in Europe, I also want to ensure that my prefixes are not advertised to Asia, because we know that there may be congestion between Europe and Asia. So we want to make sure, because this is an Anycast prefix, that these Anycast prefixes, when they're consumed by people in Asia, they don't traverse towards Europe. Like, they may stay in Asia, they may go to Europe. That will depend on many, many factors, but we want to ensure that they don't go towards Europe. And of course, like, this abstraction is hiding all the details about the communities. Like this is going to translate to, I don't know, like 30, 40 different transits across Europe. And this system is just going to resolve all those communities on the operator's behalf. Then finally, on a particular switch, you may want to prevent like a particular peer to not get your prefixes, because you know that that peer doesn't have the capacity or it's having some issues. So you can say like, OK, this particular peer connected on this particular IX, do not announce my prefixes, because I would rather that peer to get the traffic via their transit, because they don't have capacity on the IXP. If that had been a real example, it would have generated around 25,000 different advertisements across the entire fleet. So this is a huge improvement for network operators. Like, they have like a 10, 15 YAML file, and that generates like a massive amount of prefixes that they don't really have to care about. And now, like, having abstractions is great because it allows you to operate things in a saner manner, but mistakes can still happen, right? Like, you may like mistake a region with another one, and things may blow up. So you need a way for operators to describe like certain conditions that must never be violated. So I don't want to get into too many details here, but this would be an example where the operator would be saying like, OK, on all my sites, for all of my prefixes, I want to ensure that they are all announced either bytelia and or entity. So if these constraints is violated, like the entire pipeline that deploys the changes should just stop. Like shouldn't allow me to do this. Okay, so now we have all these systems in place. We have this YAML file. We have this orchestration system. All these tests. Now we need to kind of put everything together. So we need a workflow that allows for peer reviewing changes because we want to ensure that a human doesn't make a mistake, so it's better to have like a second human reviewing that change. We want to run automated tests, so all these constraints that I was mentioning before needs to be validated. And then finally, we want to deploy everything automatically. So let's see how this workflow looks like. So you have an operator that sends a PR to like a GitHub repo. This, like GitHub will just notify Jenkins, so Jenkins starts like running tests. Now a second operator can review this PR and approve it if it looks good. And then when the PR is merged into master, Jenkins is again notified, and then Jenkins will just like deploy the changes across the entire fleet. The good thing about using GitHub instead of some like web form, web UI, whatever you want, is that you get a lot of things for free. Like you get like history, like you can actually go there and see like who changed what and why. You get rollback as well, like built in. So if there is an error, you can just go there like, okay, like undo this as quickly as possible. You also get diffs, which is nicer to review. And then of course you get all these inline discussions and comments on the same pull request. So yeah, we're almost done here. In summary, it's a miracle the internet actually works. Like the amount of complexity in here is insane. So I'm actually surprised that there are no more outages on the internet. Abstractions is a really, really good way to provide operators to focus on problems rather than on how to implement the solution to that problem, because I mean you're under stress, you want to solve a problem. You don't care if it's like you have to set local pref, you have to set med, you have to set this community, you have to connect to that other, so you just want to solve that particular problem. You want to avoid sending traffic via a particular region of the world. And even though abstractions simplify things, you still need safeties to allow operators to make changes fast and without fear. Like it's very common, like especially in the service provider space, like every change needs to be notified 30 days in advance. Like you don't want that, especially not if you need to operate under a DDoS attack or something like that. And then finally, like processes and workflows is sometimes like a dirty work. Like people get super scared, like, oh yeah, there's so much process, everything is so slow. I completely disagree with that. Like processes and workflows should be there to facilitate things, not to be on the way, which is not always the case, to be honest. But like a good process and a good workflow like should just empower you to do like things better and faster and safer rather than just slower. And that's pretty much it. If anyone has questions. Is someone microphone?
Hi, I have two questions. Number one, can you say more about safety checks? And question number two, do you provide this solution as an open source solution?
So there is a lot of business logic here. So okay, so for safeties, we are running our own code. The thing is that there is a lot of business logic here. Like, what does it mean for us to announce this thing or whatnot? Actually, the business logic is not on the how you call it, on the logic to do the safety, but on how to retrieve the data. So it's retrieving the data from all of our backends and whatnot. So yeah, it's a lot of custom code that I don't think it would work anywhere else because you don't have our backend with our data. You have a second question?
The second question was, do you provide it as open source solution?
For what?
The software that you showed.
So it's the same problem. Like I could open source everything, but the problem is that the data that I'm using, it's not going to have the same format of your data. Like, to provide this service, you need to download from somewhere like where all your peers are, all the peer groups, routing policies, the communities that they use for this and for that. So our backend is again, it's built in-house. So I could open source everything, but then you would have to somehow model all your data to match our data. So I don't know how worth it would be.
I have third question. Probably the last one. So your system use Git for peer review and publishing, versioning, rollback and stuff. The question is if it's ready to implement automation changes. For example, you have some kinds of issue with peer, and it's quite obvious that you should redraw your prefixes, and it could be automated. But with process that you showed, it takes time because it must be peer review and stuff. Do you support such automated actions or not? Or you have separate mechanism?
I'm not sure I understood the question. So you're asking if, so okay, let's go back to the workflow. Just, where is it? So the only thing that is manual in this particular workflow is like the first step and the third step. Everything else is just run automatically, right? So the operator sends the PR, and then like the tests are just run like automatically. So Jenkins will just notify back GitHub like, oh yeah, the tests are good to go. And then the second operator needs to approve it. And then when it's approved, like either the second operator or the first one, doesn't really matter, will just like merge the pull request. And then the rest will just, again, happen automatically.
Okay, so example, you have, for example, a prefix leak, and you somehow, or your tools detected that the prefix leak is from provider X in IXP Y. And obvious solution to overcome is to withdraw from this provider X. Do you have automated tool somehow around this specific, or you just make a manual decision?
You mean if a peer is sending me prefixes?
No, they leak your prefixes. Let's say a small Italian provider leak your prefixes to, let's say, Sparkle.
Oh, okay, you mean if they have like a leak.
Yes.
So we have other tools to detect those cases, and we haven't integrated those tools into this workflow yet, but the operators will get notified and they will take like immediate action. But yeah, like we try not to conflate like many services together. Instead, we try like to compose them somehow. So it may be like in a few months from now or a year from now, like we start like leveraging that tool to send a PR directly here. So the operator only needs to approve and merge. But today, like we have alerting for the operators and then this process to kind of like expedite the changes.
Jeszcze ktoś chciałby o coś spytać? Nie? Dzięki w takim razie. Thank you very much.
Well, thank you.